Hi, let's continue with our section. In this video, I will introduce to you probability distribution. So, a probability distribution is a mathematical object that describes how likely different events are. In general, these events are restricted somehow to a set of possible events such as 1, 2, 3, 4, 5, 6. For that, we exclude undefined. A common and useful conceptualization in statistics is to think the data is generated from some true probability distribution with unknown parameter. Then inference is the process of finding out the values of those parameters using just a sample, also known as a dataset. From the true probability distribution in general, we do not have access to the true probability distribution, and thus we must resign ourselves to create a model in an attempt to somehow approximate that distribution. Probabilistic models are built by properly combining probability distributions. And now, if a variable x can be described by a probability distribution, then we call x a random variable as a general rule. We people use capital letters such as x to indicate the object's random variable and x to indicate an instant of that random variable. X can be a vector and thus contains many elements or individual values. X equal x1, x2, xn. So let's see example of using Python. Our true probability distribution will be normal or Gaussian distribution, which means mu equals 0 and standard deviation equal 1. So these two parameters are completely and unambiguous define a normal distribution. So using SkyP, we can define a random variable x by writing state.norms mu and standard deviation, and we can get an instant x from it using a RVS random variables method. So in the following example, we ask for three values. So we define a mu equals 0, and then standard deviation is equal to 1, x equals state.norm, and then we got is the random variance method in here. And you will notice that each time you execute this code in StackSpeak, every trial you will get a different random results. Notice that once the values of the parameters of a distribution are known, the probability of x value is also known. What is random is the exact x value you will get at each trial. A common misconception with the meaning of random is that you can get any possible value from a random variable, or that all values are equally likely. The allowed values of a random variable and their probabilities are strictly controlled by a probability distribution, and the randomness arises only from the fact that we cannot predict the exact values you will get in each trial. Every time you execute a above code, you will get three different numbers, and if we iterate the code 1,000 times, you will be able to empirically check that the mean of the sample value is around 0, and that 95% of the samples will have value within the negative 1.96 to the positive 1.96 range. Please do not trust me. Use the Pythonic powers and verify it by yourself. We can arrive at this time conclusion if we study mathematical property of normal distribution. So a common notation used in statistics to indicate that a variable is distributed as a normal distribution with a parameter mu and standard deviation is. So we got this notation in here. So in this context, where you find title symbol say is distributed as. So we will meet several probability distribution in this course, and every time we discover one, will take a moment to describe it. We started with a normal distribution because it is like the genesis of the probability distribution. Genesis of the is like the zeros of the probability distributions. A variable x follows the Gaussian distribution if its value is dictated by the following expression. So px, mu, and standard deviation, we got 1 divided by standard deviation times the square root 2 pi, and then we got the time to the power of e. We got zx x minus the mean square divided by the 2 standard deviation square in here. So this is the probability density function for the normal distribution. You do not need to memorize the above expression. I just like to show it to you. You can see where the number come from. As we have already mentioned, mu and standard deviation are the parameters of the distribution. And by specifying those values, we totally define the distribution. So you can see the expression above as the other term that as on constant. So we can take any real value, and that is we belong to R, and dictates that the mean of the distribution and also the mean, median, and mode, which are all equal. Standard deviation, which can only positive, and dictates the spread of the distribution. The larger the value of standard deviation, the more spread out the distribution. So since there are infinite number of possible combinations of mean and the standard deviation, there are an infinite number of instances of Gaussian distribution, and all of them belong to the same Gaussian family. There are two types of random variables, continuous and discrete. Continuous variables can take any value from some interval, so we can use Python plots to represent them. And discrete variables can take only certain values, so we can use Python interpreters to represent them. The normal distribution is a continuous distribution. So now is a good time to talk about independently and identically distributed variable. So many models assume that successive values of random variables are all sampled from the same distribution, and those values are independent of each other. In such case, we will say that the variables are independently and identically distributed IID variables for short. Using the mathematical notation, we can see that two variables are independent. So bxy equal bx times by for every value of x and y. A common example of non-IID variables are temporal series, where a temporal dependency is a random variable is a key feature that should be taken into account. So now is a good time to talk about Bayesian theorem. So now that we have learned some of the basic concepts and jargons from probability theory, so we can move to the moment everyone was waiting for. Without further ado, let's contemplate on its majesty Bayesian theorem. So we got P theta y equal by theta times b theta divided by by. So well, it's not that impressive, is it? It looks like an elementary school formula, and yet paraphrasing Richard Feynman, this is all you need to know the Bayesian statistic. So learning where Bayes theorems come from will help us to understand its meaning. So according to the product rule, we have is b theta y equal b theta y times by. So this can be written as b theta y equal by theta times b theta. So given that the terms on the left are equal, and for both above equation, we can combine them and write like this. So this is the result that we have compiled them. And if we reorder the above equation, we'll get the expression top equation, which is the Bayesian theorem. So now let's see what the first formula implies and why is it important. First, it says that b theta y is not necessarily the same as by theta. So this is a very important fact that one that is easy to miss in daily situation even for people trained in statistics and probability. Let's use a simple example to clarify why these quantities are not necessarily the same. The probability of a person being a Bob, given that this person is Argentinian, is not the same as the probability of being Argentinian, given that this person is a Pope. So, as there are around 44 million Argentinians alive, and a single one of them is currently Pope, so we have Pope P Pope equal P Pope Argentinian, so roughly equal 1 divided by 44 million, and we also have P Argentinian of pop is equal to 1. So let's replace so if we replace theta with the hypothesis and y with the data, Bayes theorem tells us how to compute the probability of a hypothesis theta given the data y, and that is the way you will find the Bayesian theorem explained in a lot of places. But how we do turn the hypothesis into something that we can put inside the Bayesian theorem? Well, we will do it by using a probability distribution. So in general, our hypothesis is a hypothesis in a very narrow sense. We will be more precise if we talk about finding suitable value for parameters in our models, that is parameters of probability distributions. By the way, we don't try to set theta statements such as unicorns are real unless you are willing to build a realistic probabilistic model of unicorn existence. So Bayes' theorem is essential to the Bayesian statistic, and we will see later using the tools such as BY, MC3 free ourselves of the need to explicitly write the Bayesian theorem every time we build a Bayesian model. Nevertheless, it's important to know the name of each part because we will constantly refer them, and it is important to understand what each part means because this will help us to conceptualize model. So let's do it. So we got p theta is a prior, by theta is a likelihood, b theta y is a posterior, and by is a marginal likelihood. So I will explain all of them. So the prior distribution should reflect what we have known about the value of the theta parameter before seeing the data y. So if we know nothing like Jones-Snow, we could use flat priors that do not convey too much information. In general, we do better than the flat priors as we learn in this course. The use of prior is why people still talk about Bayesian statistics as subjective, even when priors are just another assumption that we make when modeling, and hence are just as subjective or objective as any other assumption such as likelihood. So the likelihood is how we will introduce the data in our analysis. So it's an expression of the plausibility of the data given the parameters. So in some text, you will find people call this term sampling model, statistical model, or just model. We will stick to the name likelihood, and we will call the combination of priors and a likelihood model. So let's talk about posterior distribution is a result of the Bayesian analysis and reflects on that we know about a problem given our data and model. So the posterior is a probability distribution for the theta parameters in our model and not a single value. The distribution is a balance between the prior and the likelihood. So this is a well-known joke. Bayesian is one who while expecting a horse and catching up the glimpse of a donkey, strongly believes he has seen a mule. So one excellent way to kill the mood after hearing this joke is to explain that if the likelihood and bias are both vague, you get a posterior reflecting vague beliefs about seeing a move rather than the strong ones. Anyway, I like the joke and I like how it captures the idea of a posterior being somehow compromised between the prior and the likelihood. Conceptually, we think of the posterior as the updated prior in the light of new data. In fact, the posterior from one analysis can be used as the prior for the new analysis. This makes Bayesian analysis particularly suitable for analyzing data that becomes available in sequential order. So some examples could be an early warning system for natural disasters that possesses online data coming from the meteorological situations and satellite. So, so the last term is the marginal likelihood, also known as evidence. So formally, the marginal likelihood is the probability of observing the data average over all the possible values the parameter can take as described by the prior. Anyway, for most of this code, you will not care about the marginal likelihood, and we think of it as a simple normalization factor. We can do this because when analyzing the posterior distribution, we only care about the relative values of the parameter and not their absolute values. So if we ignore the marginal likelihood, we can write the Bayesian theorem as a proportionality like this. So we got the probability of theta or y proportional to the probability of y or theta and then times the probability of theta. So understand the exact role of each term in Bayesian theorem will take some time and practice, and it will require us to work through a few examples. And that is what the rest of this code is for. And that is all in this video. So I hope you enjoy it, and I will see you in the next video.